Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about SN2 reactions. And so to start with, I'd like to start with the analogy of the cat in the comfy chair. All right, so here you are. You are this orange cat, and there is a gray cat in a nice comfy chair. And you want that comfy chair. So there are two things you can do if you are this orange cat. The top one here is the first possibility. You can wait for that cat to get tired or to stretch or get water or something and leave, and then you can steal his spot. Okay, that's one possibility. Second possibility is you can say, all right, I'm just gonna take this right now, and I'm gonna push the gray cat out of the comfy chair. Look how upset he is. And then I can steal that all for myself. All right, an SN2 reaction in analogy form is a lot like this second possibility. All right, so what exactly am I talking about? An SN2 reaction is a very common organic chemistry reaction where a bond is broken and a bond is formed all at the same time. So here's a real example and a representation of it in ball and stick form. I have CH3SH, which is called methane thiol, and I have CH3I, which is called iodomethane. So you can see this guy right here, that is our methane thiol, and this right here, that is our iodomethane, okay? Notice that the yellow thing, that is gonna be the sulfur, and this purple thing, that's gonna be the iodine. So what happens is, this guy, this sulfur, has some lone pairs of electrons. It's gonna get super, super close to this carbon. When it does that, you can see that a bond is starting to form between these two things. That's what this like green thing is. It's a bond forming. This red thing is a bond breaking. Notice that carbon does not want to have 5 things around it. Okay, remember it only wants 4 things. So you can see here we have a nice trigonal pyramidal shape to our carbon and our hydrogens. Right here, it is being stretched beyond its limits. So this is trigonal planar, and it does not want to have this trigonal planar shape with, 2 other things attached to it. So the only thing to do is for this guy to leave and for this bond to form, and now we're back to a nice trigonal kind of pyramidal shape again on this, which ends up being tetrahedral. But you can see kind of that shape here at the bottom. All right, that's an SN2 reaction. It was really hard for me to not use these vocabulary terms while talking about the example I just showed you. Okay, so we got to go over the vocabulary. First thing you got to realize is that all SN2 reactions have 3 parts to them. You have a substrate, otherwise known as an electrophile, and that is your starting reactant. So that would be this. This is our substrate in our picture here. A nucleophile is a chemical that can donate an electron pair and form a chemical bond. That's going to be the Nu with a negative sign. And then you also have a leaving group. A leaving group is whatever fragment is left over because the bond has broken. So you can see that L here is going to be the leaving group because it ends up leaving at the very end. So in our analogy of the cat in the comfy chair, this is our comfy chair. This is you. You are the orange cat, and you're going to push this guy, which was the gray cat, out of the way. It's sometimes called a backside attack because literally this attacks the backside and then this gets pushed away, all right? And so every SN2 reaction has those 3 parts to them. Again, just think of the analogy of the cat in the comfy chair. All right, next up. What is the mechanism then that we're using to do this? Like I said, it's called a backside attack for a reason, but the important thing is the substrate and the nucleophile are involved in the rate determining step. So the substrate is important, the nucleophile is equally important. They're both important. If you wondered why it's called an SN2 reaction, the 2 is representing the substrate and the nucleophile. It is bimolecular, which is where the 2 in SN2 comes from. And so again, the mechanism is you have your nucleophile. There's a backside attack. This forms an intermediate there where you have this bond forming and this bond breaking at the exact same time. And then at the very end, you're left with your leaving group all by itself and you have your product. That's the mechanism. All right, let's go into some details. What makes for a good nucleophile? If you want to do this reaction for yourself, you have to pick a good nucleophile. Nucleophile literally means the lover of the nucleus. Phile meaning love, and then nucleo meaning nucleus. So if you're a nucleophile and you love the nucleus, that must mean because the nucleus is positive, you must be negative, or at least strongly partially negative. Okay, if you have a partial charge, that's okay too. Conjugate bases make great nucleophiles. If you don't remember what a conjugate base is, you take an acid and you remove an H plus from it. When you do that, you're left with a conjugate base. So conjugate bases can be things like chloride ions or nitrates, hydroxides. Those are all great conjugate bases. The stronger the electronegativity of your nucleophile, the less effective it becomes. So on this list, this is your best conjugate base slash nucleophile. And as you go down here, it gets more electronegative, and so it's going to end up being less effective. Fluoride being the most electronegative thing, and so it's going to be a weaker nucleophile than this guy would be at the top. All right, those were the nucleophiles. Let's talk about what makes a good substrate, what makes a good electrophile. So if you are trying to pick an electrophile, alkyl halides are pretty much your only choice. Alkyl halides are great, and any related compounds to it are the best substrates. Okay, if you don't know what an alkyl halide is, this is an alkyl halide, this is an alkyl halide, and this is an alkyl halide. So X could be any halide, any fluoride, bromine, chloride, iodine, anything like that, that would be your X. Then you have a carbon, you have some hydrogens, and then R can be anything. Okay, R can be a hydrogen, or it can be a carbon attached to something else. So this is called a primary because it only has one other thing attached to it other than these two hydrogens. Okay, secondary, notice it has two groups attached to it and a hydrogen. Tertiary, you have three things attached to it. So alkenes and alkynes, so double and triple bonds, do not undergo SN2 reactions. They go through a whole different process. And so if you see a double or a triple bond, realize that you're not going to have an SN2 reaction. The thing that I was trying to point out with the primary, secondary, and tertiary is a concept called steric hindrance. So steric hindrance inhibits and slows down SN2 reactions. So a primary halide is your best bet. Remember, you have a backside attack. You want to have a nice clear area back here for your bond to form. The more stuff you have attached to it, the more steric hindrance, the more difficult your reaction is going to be. So primary is much better than secondary, and secondary is 10 times better than a tertiary type of alkyl halide. What about your leaving group? What makes for a good leaving group? Leaving groups also tend to be really good if they are nice conjugate bases, but leaving groups need to be stable on their own. They have to be able to survive on their own outside of your substrate. Like I said, weak bases make for great leaving groups. Here are some examples of some excellent leaving groups. Notice, again, we have our nice weak bases here, and they all have negative charges. Strong bases are the worst choice, okay? There's a reason why you don't see alcohols starting SN2 reactions. They might be the product, but they're never the substrate. And that's because alcohols would have to basically get rid of an OH minus group. Hydroxide is a very strong base, and it's never going to work as a leaving group. So in conclusion, what's going on here? You want to have a primary alkyl halide with a weakly basic leaving group as your substrate. So a good example, chloromethane. It's a primary alkyl halide. It has a weakly basic leaving group, Cl. You want to have a negatively charged conjugate base as your nucleophile, something that has a lone pair of electrons that can make a bond form between the carbon and itself. So a good example of that, let's add hydroxide. Look at how many lone pairs of electrons it has, and it's negative. When you do your reaction, you want to have a stable product and a stable leaving group. So what would be your product of this? So notice the O would get super, super close to the carbon. It would start to form a bond, and then the chloride would end up giving up and popping off as a leaving group. So you end up making methanol. Methanol is extremely stable, okay? And you make a very nice and stable leaving group, which would be, in this case, chloride. So again, looking at this picture, everything that we talked about is followed. You have your nucleophile, you have your nice substrate with a leaving group, and then your products are nice and stable at the end. So hopefully you found that at least, if not entertaining because of the analogy of the cat in the comfy chair, educational. And if you have any questions, make sure that you ask.